Thank you very much and welcome everybody to the talk today. I hope you'll find it interesting and hopefully I won't stutter too much. That's my main objective. So today I'm going to talk to you about space geodesy. As Tamara's introduced at the Space Geodesy Facility down in Hurstman Zoo as part of the British Geological Survey. So I'm just going to give you a brief zip through what is geodesy. Simple one slide. I mean, we're going to zip through time incredibly quickly, just to say where it came from and an overview of the geodetic techniques that we now use before we go on to satellites and what they're telling us and how important they are. And that will get us to the Space Geodesy Facility and the work that we do. And I really want to give you a brief introduction to satellite laser ranging and introduce this thing called the International Terrestrial Reference Frame, which is critical. And then we'll stop off at absolute gravimetry because that's my expertise. We'll discuss the current technology and how we use it, and also some of the exciting new gravity sensors that are in development in the UK and what they might mean in the future for geodesy and Earth observation, essentially. So the first question I usually get asked for those outside geodesy, and I recognise probably some of you are inside, so forgive me for going over this again, but geodesy is essentially the study and measure of our planet through three temporally varying products: the shape of the Earth, the orientation of the Earth in space, and the gravity field. And one of the things that we push towards is this precise positional information on the surface of the Earth to millimeter level to really enable Earth observation techniques and products. So historically, humans have been interested in the shape of the planet for a long, long time. I mean, the ancient Greeks were a little bit obsessed with spheres and perfection of spheres. And of course, they thought the Earth was a perfect sphere. And surrounded by the solar system in perfect spherical orbits around the Earth. It's the center of the universe. And that belief held sway for a long, long time. And when this clever chap came along in 250 BC, he measured the circumference of the Earth for the first time using simple geometry, which was quite a mean feat at the time. And he managed to get within 15% of the value that we now know. And he was a little bit over, but I think we can forgive him seeing it was so long ago. And then really Newton, we flashed through time and loads of scientific progress to Newton, and he didn't really believe in the spherical Earth because he was looking at pendulum measurements made by Richter, different, obviously a little bit obsessed by gravity as well. I quite like Newton. And then again, flashed through loads of scientific development and thinking to 1959, and this quite pivotal guy called group called King, Healy and Nearson published a paper based upon the first man-made satellite in space called Sputnik and the orbit of that satellite and what it meant for measuring the Earth and telling us information about our planet. And they managed to obtain a ratio from the polar diameter and the equatorial diameter to give this flattening ratio, and they gave us the currently adopted radius of the Earth at the same time. And really from that point onwards, there was a huge push to use satellites for looking at the Earth in optical and radar observations. And then NASA started their crustal dynamics project to monitor our dynamic Earth. I mean, our Earth is being pushed and pulled by so many forces on a daily basis, or a sub-daily basis, obviously. That they really push forward the technology, research the technology of how to monitor things. And by the late 60s, we had two geodetic techniques called satellite laser ranging, which we'll be going into quite in detail a little bit later, and very long baseline interferometry. And one of the first things they did with those two geodetic techniques was confirm that the North American tectonic plate and the Eurasian plates were moving apart at approximately a rate of 17 millimeters per year. So given the time frame we're talking, the late 60s, early 70s, that's a already a huge step forward in how we're using satellites at that point. Then following along in the 80s and 2000s, two more geodetic techniques were added. So global navigation satellite systems, or GPS, some people know it as, because that was the first system from the Americans put up. And this thing called DORIS, which is Doppler orbitography and radio positioning integrated by satellite. And DORIS, GNSS, and SLR are all using man-made satellites in orbit to tell us information about our planet. And some of those satellites, I just want to go through the classifications of those satellites and what they're really telling us and why they're important. So they're one of the primary satellites for our work at the Space Geodesy Facility is these things called geodetic satellites, which I'll go into all of the classifications in a minute, but geodetic altimetry, so they're measuring the planet, telling us something directly. Navigation satellites, they're your GNSS satellites, they're telling you where you are, whether, we use them all the time, whether in a car sat nav or on your phone to tell you where you are. And then gravity satellites telling us gravity maps of the planet, which it's relatively new science. The first dedicated gravity mission was the 1990s. And then also topographic mapping research and other satellites that don't really fall into distinct categories as I've got them here. And we can talk about they can mainly be put into these classification of orbits. So high to Earth, medium to high Earth orbits, navigation satellites. And these altitudes that I've quoted are very rough, but approximately 20,000 to 42,000 kilometers. Medium Earth orbits, 6,000 to 18,000. Those two geodetic satellites, I'll obviously talk about in a minute. And low Earth orbit satellites are approximately 350 to 1,500-ish. And low Earth orbits are really critical to tell us information that we really need to know all the time. So giving us information on ice cap melting, what that means for us, how the Earth is rebounding back into a sphere from all that weight of the ice melting, giving us information about how that, more water content from the ice caps and the glaciers melting is affecting the oceanographic ocean temperatures and currents, and as I said, the gravity field, river flooding and deforestation, and mean sea level. Obviously, as the glaciers and the poles are melting, all of that water will mean our mean sea level is increasing, and that has a huge impact for us as humanity. Seeing how projecting 50, 100, 150 years into the future to see what parts of the land mass that we currently take for granted are going to be underwater, or even if we look at it very locally in the UK, how much of London we can save in 50, 100 years time, or how high we need to rebuild the Thames walls, the walls along the Thames to actually protect the City of London, or the Thames Barrier even, that's not going to be as high enough forever, so they're going to have to rebuild that somewhere. How much of London can we save, and how much of the outlying things in 150 years that we can't. So it's really important science. This is a graph using altimetry satellites to estimate mean sea level using a whole host of analyst centers. So this is multiple altimetry satellites, because we go from early 1990s to close to now, 2019-ish. And all of those different satellite missions, and we're probably talking at least 4 or 5 here, are telling the same story. So all of those analysis centers are saying that mean sea level is increasing at approximately a rate of 3.3 millimeters per year at the moment. So we can use that and forward project, or people doing that kind of analysis can anyway. And then, as I mentioned, these geodetic satellites, these pretty critical for Earth observation. They are primarily the Lagos and Etalon satellites. So there's 2 Lagos and 2 Etalon satellites, and they are inert spheres in space in incredibly stable Earth orbits. And one of the primary products from those satellites, or the tracking of those satellites, is the contribution to something called the International Terrestrial Reference Frame, which is incredibly important, and I'll discuss later on in the presentation. And it also drops out of tracking those satellites, the size and shape of the Earth and post-glacial rebound, as I mentioned, the Earth rebounding back into a sphere, polar rotation, tectonic plate movement, and variations in the length of day. So every day it's varying by milliseconds a day, and whether there's a trend, or we can monitor that through tracking those satellites. And then high Earth orbit, we're talking navigation satellites, and of course it's not only GPS satellites, it's well, GPS is American, Galileo European, GLONASS Russian, COMPASS Chinese, and VIDO Indian, and they can transmit continuously transmit coded navigation and clock signals, and they tell you where you are. But on the other hand, satellite laser ranging, the technique, tracks them to tell them where they are. So we tell them where they are, and they tell you where you are. So yeah, it's a it's complementary method to satellite laser ranging, and because they can also tell satellites where they are in space as well. And of course, we can't really discuss it without saying, well, hang on, why do you need tracking in the first place? Surely we can model where our satellites are in space, and actually, no, we can't. We can't model all of the forces very accurately, or to the accuracy we require to push science forward. So we have to have these very accurate tracking techniques to really determine the precise orbits of those satellites in space. And I'll show you in a couple of slides' time why that's the case. And of course, some forces we can model to some degree, and some are a bit more tricky, especially when you have a sunspot event, because a sunspot event can be a pressure wave, but it can also be a coronal mass ejection. So it's a particle storm that comes towards the Earth as well. And they can knock satellites in their orbits quite a long way. So geodesy and Earth observation go hand in hand. This is a schematic showing an altimetry satellite. So that's taking a range down to the ocean, taking other measurements at the same time. And GNSS satellite is telling it where it is. And so is the Doris station, and so is the laser ranging station. And this orbit that it's transcribing, and I'm hoping you can see my mouse here, the orbit determination is incredibly important, because unless you can determine that orbit very precisely and very accurately, what is the range it's actually taking? So when you're monitoring your sea level, how can you trust this range if you don't know exactly where that satellite is in its orbit? So we need observations to improve not only knowledge of the forces acting on the satellites, also determination of those, well, pretty critically, determination of the precise orbits. And from that also drops out accurate positional information of the tracking stations themselves. So we will be able to derive our station coordinates more accurately through the tracking of especially the geodetic spheres. Which, as has already been mentioned, the Space Geodesy Facility is based down in Herstmonceux Castle, which was the home of the Royal Greenwich Observatory from the 1940s to the 1990s, and we are the only scientific operational remnant of the RGO from those days. The castle estate is now known by a Canadian university and used as a study centre, so we get students go past quite regularly. And just to give you an idea, this is our site. So in this picture, drone picture, you can see our 3 offices. This is the satellite laser ranging dome. Again, I hope you can see my mouse, and you can just about see the telescope pointing out the top. We've got a radar system alongside. You might be able to just make out this tower with one of our GNSS antennas on top. The other one's off picture right over in the west over here. And there's a mound you might be able to make out as well, which underneath is a semi-sunken bunker which in the south end, so down here, is our absolute gravimetry, which I'll be talking about later. And just to give you a view of how picturesque the place is and how close the castle is, there's the castle in the background for you. So the Space Geodesy Facility at Hurstman Zoo has been providing geodetic technique measurements, sorry, for 39 years. We're now classified as a NERC national capability site, and we operate satellite laser ranging, 2 GNSS receivers, as I've just alluded to, and absolute gravimetry. And those 3 geodetic techniques feed into the big international databases and services. So the International Laser Ranging Service, the International GNSS Service, and something called AGRAV, which is the Absolute Gravity Database. But I'll be explaining that a little bit more a little bit later. And alongside those geodetic techniques, we've got a whole host of supporting instrumentation and equipment, such as a sun photometer, visiometer. We've got a BGS broadband seismometer, and test INSAR ground reflectors and the lawnouts at the front. And we've got a range of environmental monitoring equipment. And the station uses as its frequency source an active hydrogen laser, which I won't really go into anymore, but just to mention it. So, like I say, the SLR has been going for 39 years. They got their first track back in 1983. So the site itself started off as a solar observatory and was converted to satellite laser ranging in the late 70s and was operational by 83. And it provides precise tracking of Earth observation satellites. So we don't track all satellites in space. There's no need. We only track satellites that really need to know where they are very accurately. Oh, I'm sorry about the text issue there. And the SGF operates our own International Laser Ranging and Service Analysis Centre. So we provide products into the IRS and do a lot of housekeeping and quality control checks on all of the data worldwide. Of course, the network is quite large, so the International Laser Ranging Service is made up of satellite laser ranging stations across the globe, and there's approximately 40 worldwide. They are primarily run by countries who recognise the importance of the technique and the importance of tracking Earth observation satellites. And obviously NASA have got quite a few, and they run a few in different countries as well. But rather to a surprise for many people, the Hurstman Zoo, although it's in the UK, tends to be within the top few stations in the world, not only for the number of passes, but also for stability of data. So this is a screenshot of an ILRS product saying that we were 4th in the world for a total number of passes from 2020 to 2021. We can't compete, unfortunately, with the likes of Yarragiddy in Australia, who basically trounced everybody in the entire network. But you know, I think 4th for being in the UK is pretty good. We achieve that essentially through, we've got a dedicated staff team. There's only 6 of us, but we all do the observations and are quite reactive to skies clearing, and we come in and do our shifts. So I think we probably need to back up a step and say, we've discussed this thing called satellite laser ranging, but what we haven't said is what it is. And satellite laser ranging is essentially, it's an incredibly simple theory. It's you fire a short pulse laser at a satellite in space, which was equipped with a mirror assembly, so a retro-reflector assembly, which a retro-reflector assembly is made up of corner cubes that reflect light back at the point of source. So an array is made up of a number of corner cubes. And you will know what a corner cube is or a retroreflector is because you see them every day. There are street signs, there are cat's eyes on the road, there are your bike reflectors or your car reflectors. So we know, everybody should know what a retroreflector is, but you may not know the correct name for it. So essentially what we do is we time tag a pulse going out of our laser. It fires up to a satellite in orbit and then bounces off the mirror and comes back to us, and we time tag it as it gets back. And then we do that many, many times over the arc of the orbit. We see that satellite above the station. And from that, we essentially can measure a two-way time of flight to the satellite and back. So from that, we can accurately determine the distance to the satellite. Simple, absolutely simple. Okay, it's not quite so simple as that when you get into practice, but it's, I don't know, good fun, I suppose. So some simple satellite laser ranging facts for you. At the Space Geodesy Facility, we have a transmit telescope and a receive telescope. So again, if you can see my mouse, the transmit is on the right-hand side of the main telescope, and the main telescope is the receive. And this thing on the back, which is orange and black, is a wide-angle camera. So the laser downstairs fires up and is bounced off a number of mirrors to come up to the telescope and be transmitted from this transmit telescope. And we are using a laser that fires around 1,000 times a second. Each pulse is 10 picoseconds long, which translates to about 2 millimeters long. And in each pulse is about 1 × 10⁻15 photons. And in the laser bed, there is a start signal. So it detects the photon going out. And then the photon gets emitted, travels through the atmosphere, hits the small proportion of those photons will hit the retroreflector in space and get bounced back. We will collect them in the main telescope, and they will trigger off the detector on the back of the telescope. And therefore you get your two-way range. So you can work out where your satellites are very accurately from that simple process. And the real trick is it's night and day. So we track 24/7 in clear skies as long as the budget allows. And to do that, you need a lot of not only spectral filtering. So we know the precise wavelength for laser, and we've got filters that go in around that to try and cut down on the amount of noise that we will get. So sunlight is a noise source for us. So we use those spectral filtering to cut down on that, and also temporal filtering. If we had a detector that was open constantly, it would just be flooded with noise and sunlight coming back into it. So what we've actually got is a detector that wakes up for a very short period of time, gobbles 1 photon and 1 photon only, and shuts back down again. And so it's doing that Pac-Man kind of gobble 1,000 times a second. And for each one of those events, it's only open for 200 nanoseconds. So on the black side of this screen on this slide, this is what the observer will see. And you can see here is a 60-second window in time snapshot. And on the upper plot is the entire pass. So you can see when this was taken, the pass hadn't ended because there's the black zone. So this is pass that's gone on, and this is still to go. And there's a rolling window on the lower screen. So each one of these white points is a noise point or a return from our laser, or a return from our satellite, I suppose I should say. So you can clearly see where our laser is coming in. And all of these noise points are just confusing it slightly. And this zip of more intense noise is most probably a little bit of light cloud. It's just reflecting off the cloud a bit. And then I just wanted to show, because of the nature of what we do at Hurstman Zoo, a Space Geodesy Facility, and I'll explain in a couple of slides' time, we use single photon. So I just said, if I go back one, we routinely range and we expect one photon back at about 25,000 kilometers. And what that means is for low Earth orbit satellites, we can change the size of the beam in space to statistically control the return rate as well. So we don't want the detector flooded with noise. We want to maintain a statistical rate of 1 photon. And what that means for the satellite track is that you can see features actually within the track. So this is a different satellite than this one, unfortunately. But Andy Castor was a test satellite with just, I think it was 4 retro-reflectors on it, and it was tumbling in low Earth orbit, very low Earth orbit. But what that means is when you're single photon, you can see all of the retro-reflectors actually, you can see the satellite tumbling because the retro-reflectors are going in and out of what we actually see, which is interesting if nothing else, and things can be derived from that, and it has been used in the past for working out tumbling rates of satellites, etc. So this thing I've just mentioned, which is a single photon, it gives us more information about the center of mass of the satellites. And at the SGF, we've done a lot of work over the many years of providing better estimates to the whole of the community to center of mass corrections. So as I might describe, there's 40 stations approximately worldwide, and they're all using different technologies, different detectors, different lasers, etc. So and they can use multi-photon returns or single photon returns, and essentially what we've done is loads of work on what that actually means for the center of mass corrections for those satellites. And the center of mass is where the scientists analyzing the data will use their data as the point, as the source, basically. So to recap slightly, because it's a concept that if you're familiar with, you can understand easily, and if you're not familiar with, it's maybe slightly hard to describe. So we're tracking these satellites in space that are telling us about the Earth. So in the case of altimetry satellites, they use radar, or may use radar, to measure the distance down to the ocean and land surfaces, ice surfaces. And we track them by satellite laser ranging, or GNSS. We might have to track GNSS on board, to determine the precise orbits of those satellites, so that we can essentially, scientists can use that information to tell us about what's going on with our dynamic Earth. And as a product of that, we also get our tracking station coordinates very accurately. Now, all of that requires a reference frame, and this thing called the International Terrestrial Reference Frame comes in. If you want to use satellite measurements in space, then you have to have a reference frame to really make sense of it all. And to impact Earth observation science, that reference frame has to be millimeter accuracy. And there's pushes to get that more and more accurate from the scientists who are actually using the data itself. Now, the ITRF is actually comprised of all of the geodetic techniques. So satellite laser ranging is used for the origin, so the geocenter of the Earth, and it's uniquely just SLR is used for that, primarily LAJOS and LAJOS 2. And the scale is derived through a combination of SLR and VLBI, and orientation uses the 4 big ones: VLBI, GNSS, SLR, and DORIS. And the ITRF is recalculated and computed on a few year basis to improve it each time. And we're using more and more techniques to actually go into it. And the SGF provides, the analysis service provides an input into the ITRF. And of course, as I've said, the Earth observation scientists are basically want more and more of it out of the ITRF, and request for 1 millimeter accuracy and stability of 0.1 millimeters per year. And that means you need multi-technique stations and more research about potential local error sources. So if there's any unmodeled factors that are going into our station position that might influence our station position, we need to know about them. So at the Space Geodesy Facility, as I've mentioned, we've got 2 GNSS receivers, Hurst and Hurt, which are IGS sites, which I won't really talk about very much, but we've also got HERO, which is an Ordnance Survey GeoNet receiver as well. And then we move on to nearly my favourite subject, I suppose, the absolute gravimetry measurements. So the objective of adding absolute gravimetry to the SGF was to characterize and identify any unmodelled signals. So any unmodelled signals that might be influencing our station coordinates, as I just mentioned. And we can also use it to look at the vertical height products of both SNR and GNSS. And the original objective was to try and see any glacial ice static adjustment of UK uplift or rate. Now, I can't remember whether I mentioned that already, but just to explain quickly, as the poles are melting and the Earth is rebounding back into this sphere, the tectonic plates are all adjusting on the surface. And one of the impacts of that is this thing called glacial ice static adjustment. And in the UK, that means that the UK is starting to tip. So Scotland's going up and the south coast is tipping downwards. And absolute gravimetry can be used in theory to show you that. And we contribute into this thing called AGRAV. And because of the way we're using absolute gravimetry at the SGF, we're using it fairly uniquely. It's run as on a weekly basis as often as I possibly can, with downtimes for servicing or comparisons, which I won't explain here. And because of that, we've been accepted as a core status in something called the International Terrestrial Gravity Reference Frame, which is currently in development in the working group that I'm in, and will complement the ITRF to eventually, hopefully, produce the global geodetic reference frame. But there's a slight digression. So the ITGRF will use AGRAV to get all of those points essentially. And the time series you can see here I'll put up, and you can see the gaps we've got in it, and you can see periods where it's a lot more or a lot less precise, and periods where the data is quite precise. And some of those we understand and some of them not so much. It's quite an interesting time series when you actually analyze it. Again, I'm not going to go into that in heavy detail here because I simply don't have the time. But this is a snapshot. So if you take the SLR vertical height product and the GNSS vertical height product, and you convert gravity, so by a simple multiplication factor, you can look at the three geodetic heights compared to each other. And this is new. So this, I've not done statistical analysis of this is brand new. I just wanted to show you. But the interesting thing for us is that it shows the site is fairly stable. All of the geodetic techniques are in the same kind of bandwidth. So what I've done here is essentially for each height product, I've taken a mean of the time series and essentially just plotted them, use that average to take it away. So you get a height change over time, and then done that for each technique. Then this is what you get, and they all sit over each other, which is, I don't think any of us were expecting. But again, this is new and quite exciting stuff for me anyway. The instrument we're using is an FG5 absolute gravimeter, which measures gravity to 2 microgal. Again, I don't expect many of you to have ever heard of a microgal, but to convert that into SI units, it's 2 × 10⁻⁸ of meter per second squared, which again, if you convert it simply to vertical height or vertical movement, that's approximately a centimeter. So it can tell you what the crust is doing if it's moving a centimeter. It works on the principle of essentially you drop an apple and track it. So it's a bit more complicated like that. It's a little bit SLRE. It's a very simple process, but it's an incredibly complicated piece of equipment. So you drop a mass in a vacuum, you track it via laser beam, and you can derive gravity. So what actually happens is we fire a laser into a side of an interferometer, half the beam goes up off a falling mass, half the beam and then travels down to another retro-reflector in the bottom, which is providing an inertial reference frame. And that beam is then combined with the first beam to provide time-distance pairs. So it's a simple optical fringe that gives you time-distance pairs. You throw that time-distance pair into an equation of motion like you would physics at GCSE, and you can derive gravity. It's a slightly more complicated equation of motion than you might be used to, being a fourth order differential, but it's still an equation of motion, and it gives you gravity. So moving on. The types of gravity gravimeter you can get at the moment are absolute and relative. Absolute gives you a local interpretation gravity measurement, as you've just seen, and they are currently the FG5 and a cold atom only. So rather than dropping a mass, you drop an atom. And the French have a company called Mugens as the only cold atom that you can purchase at the moment. And then there's relative sensors, which basically give you a change in gravity over time, whether that's small units, which are spring-based, with a schematic here on the lower right, or a little bit more of a complicated instrument, which is a superconducting instrument, which doesn't get moved. And that provides a long time series of gravity changes, but it doesn't give you the actual acceleration due to gravity. So we measure gravity to tell us about what crust doing, crust deformation, and temporal mass change. It doesn't just tell us about one, it tells us about the two. So you've got to do a lot of calculations around the gravity measurement to tell you crust deformation only. Applications of these things, you can use them against tide gauges. So I've mentioned GIA, so how the UK is tipping. If you put it against a tide gauge and you've got sea level coming up, then you can see how the land mass is moving against the tide gauge, or you can tear apart the ocean from the land mass movements, essentially. They're used for mineral and oil exploration. So this picture, courtesy of a colleague, of a different type of absolute gravimeter in a Alaskan oil field, just monitoring how the oil's sloshing about underneath as it's pumped out. And they're also used in standards labs. So this is a snapshot of some of the things you can use absolute gravimetry for. And as the SGF, we are part of this collaboration in new gravity sensors coming through, and primarily quantum technology hub sensors. And University of Birmingham have brought their prototype one down once, which was absolutely massive. And you can see it in this photograph in the middle here. So the two FG5s are in the background with this prototype in the beginning. In the front of the photograph with the sensor head is this part here. Again, I hope you can see my mouse, and then all of the supporting electronics and laser are on this bench. And essentially, what Birmingham hope to do is give a high sensitivity, high data rate, and it'll take the place. The goal is to take the place of not only superconducting, but also absolute. So it works like a superconducting in some ways, in the fact that it's a continuous measurement, but also it's giving you absolute gravity measurements. And the photograph on the right-hand side here is courtesy of Birmingham University. This is how this prototype is now looking. That's the sensor head. I think it's quite hard to see on this photograph, but thanks to Birmingham for allowing me to use that photograph. There's not the only university researching quantum technology. So Birmingham are doing the cold atom absolute gravimeter, also gravity gradiometer, which has recently been in the news. They detected pipework underneath the ground with this thing. So it completely could revolutionize building and farming, and all sorts of things. It lends itself to huge uses. And then you've got MEMS sensors, which is micro electromechanical system sensors, which both Glasgow and Cambridge, an offshoot company called Silicon Microgravity, apart from Cambridge, are researching those MEMS sensors. The Glasgow University have been part of this thing called Newton G, which was a huge EU Horizon 2020 project with their MEMS sensor called a WEG. So they were going to deploy these things over Etna with a superconductor in the middle, not a superconductor, sorry, cold atom. So the Mugen's cold atom in the middle to find what is, try and see what's going on under Etna. These MEMS sensors could have a huge application when you define the drift and you define what's any instrumental issues with them. Then you could deploy them over. They'll be cheap. They're talking about £1,000 to £10,000 each. So you could just throw them over volcanoes, or in Africa and looking at hydrological sources in oceans. The uses are foreign. I can't describe them all. But so it's an incredibly exciting time to be part of these new sensors coming through. And we'll see how they develop over the next few years, and very much looking forward to it. And then finally, I just wanted to end on saying we've got started testing a new site in Heartland, which is quite exciting for me. It's got 4 piers down to bedrock, which we don't have at Herstmonceux because it's just clay beneath us. There's also a BGS broadband seismometer down there, and I did quite a few months of testing through 2019 and 20. Unfortunately interrupted by COVID, but at the same time I managed to install, or one of my colleagues managed to install, a test GNSS sensor down there, antenna down there as well, which has continued taking data all through all that time. So I hope to get back down there soon to carry on measurements, and hopefully we might have another mini geodetic site in the UK soon. And I think I'm around about time. So I shall end it there, and I'm sorry, it's just the FG5 at Heartland, and say questions. Thank you very much.
Wonderful, thank you so much, Vicki. That was brilliant. I'm just going to change my view. I had a question. I'm not sure if this is going to be easy or hard, or if you already sort of touched on it. Okay. But when you showed the comparison of the gravity measurements through time, through the past few years, it seemed like there were annual oscillations. Like it went up and down. The vertical change went up and down.
Yeah.
Is that to do with seasons, or and why? Yeah.
So actually, all 3 techniques show that at various points. Gravity's been very hard to see that until we really put it against the other geodetic techniques, and it's not always there. Sometimes it disappears. So we are on clay, so there's a contraction and there's a breathing of the clay through the seasons. So that's part of the theory about what's going on there. And there's hydrological implications of the site as well because of the clay. So we expect a seasonal signal essentially. Yeah.
Right, cool. So probably just the clay, but maybe not all just clay.
But there's still a lot of work to be done on. I think the SLR solution I showed is actually brand new. So this is improvement of our site coordinates beyond anything we've had. This only in the last year. So yeah.
Cool. That's okay. We have other questions as well, so I think that was a good answer. So in the chat box, Duncan Agnew has asked, do you monitor groundwater, the bane of gravimetry? I'm sorry, I find that word really difficult for some reason. Anyway, yeah. And the SLR seems to have a larger annual variation than the GNSS. Could this be because of being on top of a building? So those were the 2 questions.
Yeah, I got asked that question by somebody else today, why the SLR sees a bigger signal. And the answer is, I don't honestly know. The groundwater is obviously a bit of a bane. but it is 14 meters below us, and it varies by about 1.5 meters. So because of the clay, I've done quite a lot of testing, but small sample sizing. And the impact on the gravity time series shouldn't be massive. We're talking about sub-microgravity, actually. No, not sub-microgravity, very low anyway. And because it's a semi-sunken bunker, we've got Earth above, so that also has an effect, and there's a certain amount of cancellation out of those two signals. So you've got one pulling up and one pulled down as the ground changes and the soil moisture above. But unfortunately, we haven't got any soil moisture products sensing yet, but we've got sensors to go in the future when we've got time to put it all up, basically. So yeah, it's a bit of a pain, but the theoretical modeling says that it won't change the gravity by very much because of the nature of the clay.
Cool, that's lucky. There's a bunch of other questions, so I'll save mine till later. All right, so Kieran Began at BGS has asked, how wide is the laser beam by the time it hits the corner reflector on a satellite? And also a second question, is there a periodicity to the height measurements at Hurstman Zoo you showed earlier?
Yeah, so the footprint of the beam in space can be changed. So the Transmit telescope has a movable beam expander, and the reason we've got a movable beam expander is because we don't want to flood the telescope with returning photons from the low Earth orbiters. So something, you know, let's take a random range of 500 kilometers. If we're firing that at as collimated as beam as we can get, not only is it hard to actually acquire that satellite because it's moving quickly and the orbit predictions might not be great, but also we don't want to get all of those photons back into our telescope because of the single photon nature that I mentioned earlier. So we widen the beam up as big as we can for some satellites. And also some satellites have got sensitive equipment on board that you can't have too many photons hitting them, so you have to bring it up. So a lot of photons in those kind of instances go straight past the satellite, and we get a tiny amount come back off the mirrors. And then of course those photons got to make it through the atmosphere back to the telescope and actually be caught in the main telescope, which is, you know, only 50 centimeters. So it's quite a statistical probability thing, but we don't do too bad of a job. Sorry, what was the other part?
The other part was about periodicity in the height measurements, which I think was similar to the question I asked.
So we certainly see that in the GNSS and the satellite laser aimed mostly. And in certain points of the absolute gravimetry, though, it is a little bit more complicated.
Yeah. Cool. James Whitcomb has asked, how accurately do you know the position of the center of mass of the Earth?
Now, I don't know the exact, but I've been told by a person in the know, it's about the postage stamp size.
Wow, that's incredible.
If that's good enough for you.
Yeah, hopefully. I mean, that's good enough for me, but hopefully that answers your question, James.
Yeah.
An anonymous attendee has asked, if the GNSS measurements are in ITRF brackets ECEF, I'm not sure what all the acronyms are, how can GNSS measurements improve precision of ITRF definition?
Now, I'll have to put my hand up here and go, I'm not the person to ask this question. I unfortunately don't do GNSS analysis, so I won't be able to answer that question thoroughly enough for you. However, if you would like to email me that question, I will happily put it towards the person in the know here.
Cool. I think that sounds good. To anonymous attendee, Vicky's email address is online. Okay, Stephen Malice has asked, do you use an independent model to remove lunar solar tides from the gravity data?
An independent model as in, so all of the geodetic techniques have tidal modeling taken out. So they all need a tidal model to be removed. And actually one of the first products of this absolute gravimetry being on site was the fact that we weren't using the best tidal model that we could at the time. So we've changed that. There's still a slight tidal residual. So we are currently using FES 2000 and something. I can't remember which one. 14, I think. Which is the best we can get without having another type of gravimeter on site that we can actually determine a tidal model for us. And so it will be all of the tidal constituents, but until we get that kind of modeling, we have to use the best we can get. So
cool. Hopefully that answers your question, Stephen.
yeah, hopefully.
Yeah. Scott Johnson has asked, I think you mentioned there are 2 GNSS antennas on site. Is there processing being done with the pair, or is that primarily for redundancy?
No, there's processing done with the pair. So they're both contributing to IGS, and there's in-house analysis of the contributions of both as well.
And yeah, I guess if you want any other information about GNSS, again, you can email
Yes,
me.
I know
There's somebody on site.
Sorry,
okay.
Anonymous person.
It's okay. And Mike Floyd has asked, regarding the SLR, I might have missed it, but were the GNSS time series relative to center of mass or center of frame? Seasonal variations, particularly amplitudes, could appear different depending on the geocenter definition. I think SLR would naturally be center of mass.
I believe they're both center of mass. They were both provided to me by the same person, so I hope they are. But again, I will make a note of that and verify.
Cool. Again, hopefully, Mike, that answers your questions. If you have any follow-up questions, anybody, please feel free to ask. We're almost on time, but I just was wondering myself, with the new facility, which is built onto bedrock, will you have a gravimetry instrumentation there, and will that be better than on the clay? Or
so the site down there is a magnetic observatory.
Okay.
And essentially, I've moved my gravimeter in as because it's got pierced bedrock, and I want to test it. And the initial testing was really interesting. It's showing big hydrological signals, and that is on bedrock, so it was a bit weird. But it was big annual seasonal signals. But unfortunately, it was interrupted by COVID, so I didn't get a whole year. Right. So we're looking forward to going back, really. But it's got the potential to be a great site. So the problem with it is it's on the North Atlantic coast. So in the summer, 2 summers running, well, not 2 summers running, but 2 summers split apart by a couple of years, the data was the most precise I've ever seen in the UK. But that was when there was no coastal energy. So as the storms come in from North Atlantic, may be calm as anything in Hurstman Zoo or Heartland, but the wave energy can be transmitted in a conduction zone, so I've been told, and be transmitted to the coast. So all that wave energy hits the coast, and then the site shakes, and then the gravimeter shakes, because the bottom section is a super spring, which provides the inertial reference, but it is essentially a spring, a glorified seismometer. So any coastal energy, and the spring starts shaking. Now, in the summer, as I said, it's absolutely brilliant, and the best data that I've ever seen in the UK beats Hurstman Zoo. But in the winter,
right,
quite the same.
Yeah, cool. Okay, that's very interesting. I assume you will try and figure out a way to either figure this out or.
Well, the delight of that site is that it's because it's got 4 piers to bedrock. It could provide a comparison site for these instruments, so it could be of use to the community. But it'll take a lot more validation and a lot more testing of the site, and characterization of the site, and not only to the community, to these new sensors coming through. So one of the problems with Hurstman Zoo is that we are on this clay, and clay's a bit wibbly. Excuse the scientific parlance. And some of these sensors haven't liked it because there is just too much noise, about seismic noise here for these sensors in the basement. So this semi-sunken basement, as I mentioned, it started out life as a solar telescope, and the basement was actually where the sunlight was focused to give images of sunspots. So we're purely making use of the space that we had and converted it for absolute gravimetry. It's not particularly ideal, but it's absolutely great, actually. But apart from this bit of a seismic issue, especially for these quantum technologies coming through. So Heartland could be the answer for them.
That's so fascinating. Cool. Thank you so much. Thank you so much, Vicki. That was really super fascinating. I certainly got a lot out of it.
Thank you.
Yeah.